Hello all of you dear students, this is A.4 again. Welcome back to Rubber Duck Physics. Alright, we have come a long way and today we are going to roll right down an incline. We are continuing with rolling, but this time we are letting gravity do the work to make objects accelerate down a slope. Now remember from our last video, we discussed rolling without slipping on a flat horizontal track. Well, when we add an incline, gravity takes over, and things get a little more interesting. So, let's get into it. Gravity naturally accelerates an object down a slope, unlike on a flat surface where it wouldn't move without an extra push. There are some specific rules to rolling down inclines that we need to derive and understand. What happens at the point where we release the object? You place a ball, a wheel, or any rolling object onto the slope, and, not surprisingly, gravity starts pulling it down. The direction of the motion will be, however, determined by the slope. As the object rolls down, its gravitational potential energy, remember that's the energy it has because of its height, is converted to kinetic energy. But here's the twist. As you already know from horizontal rolling, there are two forms of kinetic energy here that get supplied from energy of height. When the object rolls, it's moving forward, that's translational kinetic energy, and it's also spinning, that's rotational kinetic energy. So we need to split the energy into two parts. We'll write it like this: m times g times h equals 1/2 mv squared plus 1/2 I omega squared. Here, m times g times h is the potential energy at the point of placement of the object from where it's released, which gets transformed into translational kinetic energy 1/2 mv squared and rotational kinetic energy 1/2 I omega squared. Now, if you are picturing it, you can see that as the object rolls down, it loses height, so its potential energy decreases. But that energy doesn't, of course, just disappear, it changes into the energy of motion. This energy splitting happens because when an object rolls, each part of it is doing two things: moving forward and spinning. Using the relation you learned between v and omega, and solving this equation for either of them, you can determine the linear or angular speed of the rolling object at any momentary height. We'll return to this later. Now, let's take a different view on the same situation. Let's invite Newton's laws and talk about the forces acting on the object as it rolls down. There are three main forces at play here: gravity, the normal force, and static friction. The force of gravity pulls the object down the slope, the normal force pushes perpendicular to the slope, and friction does something a little different. Here is what static friction does. It's what makes the object roll instead of just sliding straight down. It's the friction that creates the torque needed to make the object spin. Without it, the object would just slide, and we wouldn't have the nice rolling motion we are after. So, how do we describe all of this situation? With equations. Newton's second law for translation: sum F equals m times a. In the direction of the slope, the forces add up to m times g times sine theta minus F equals m times a. Notice that we need to know theta, the angle of the slope, to be able to move on with our calculations. And Newton's second law for rotation: tau equals I times alpha. Here, static friction creates the torque, and that torque equals F times R equals I alpha, where we denoted friction by a small f for simplicity. We can relate alpha, the angular acceleration, to a, the linear acceleration, using a equals alpha times r. When we substitute these and simplify, we get a formula for the acceleration: a equals g sine theta divided by 1 plus I over mr squared. Now, here is the key idea. The acceleration of the object depends not just on the mass or the angle of the slope, but also on the object's shape, specifically on its moment of inertia. Different objects have different moments of inertia, as you know, which makes them accelerate differently down the same slope. That's why a solid ball, a hollow ball, and the cylinder will all behave a little differently, even if they have the same mass. This equation, by the way, simplifies surprisingly while solving, and acceleration of the whole object becomes independent of the shape's mass and also their radius. It will, however, depend on the shape itself. To give you an example, for a solid sphere you get A equals 5/7 g sine theta. The solid sphere with this acceleration rolls down faster than a cylinder, and even the cylinder accelerates more than a hoop or a thin ring. The take-home message here is that shape matters. The bigger the moment of inertia, the less the object accelerates down the slope. If you have ever rolled different things down a hill, maybe a basketball and a can of soda, you'll know they don't behave the same way. Now, before we wrap up, let's repeat a key thought. Why doesn't the object slide down the slope? Why does it roll instead? This is all thanks to friction. Static friction provides the grip that allows the object to turn, rather than just slipping down. That's the reason of the fact that if the slope is too steep, the friction might not be enough, and the object will slide instead of rolling, just because of the angle. And finally, here is a little note about rolling up a slope. If you try to roll something up a slope, it will decelerate. The equations of motion are the same, but it slows down until it reaches a maximum height and then rolls back down, while its acceleration stays the same all the time. It's like when you roll a toy car up a ramp. It'll eventually stop and come back down. Let's now try to find how fast the object is rolling when it reaches the bottom of the slope, the final speed of it. This time, we can use the conservation of energy to find out. We know that at the point of release, all the energy is gravitational potential energy, and at the bottom, it's all kinetic energy, both translational and rotational. The equation we will use is m times g times h equals 1/2 mv squared plus 1/2 I omega squared. And if we substitute omega equals v over r, we can solve for v, the linear speed of the object, center of mass. The neat thing here is that the final speed depends on the object's shape and how its mass is distributed, not just the angle of the slope. So, where does that leave us? We have seen that rolling down slopes involves gravity, friction, torque, and different forms of mechanical energy. The shape and moment of inertia of the object really matter here, and so does the angle of the slope. The next question we'll tackle is, what happens when we want to consider even more complex movements, like where friction plays a more complex role than helping the round object roll by sticking it to a surface for a short moment? We are moving toward one of the coolest and yet the most demanding ideas in physics, angular momentum, and how it is conserved. Enjoying these lessons? For more in-depth, one-to-one or group tutoring, I am available online for IB DP Physics, A-level Physics, and Math and AP Physics tutoring lessons. You can get my contact info from the Rubber Duck Physics YouTube channel description field. Make sure you are using a web browser. Feel free to reach out to arrange a trial lesson. Thank you for watching the video and see you next time.